Hi, today let's discuss a few problems based on the postulates of quantum mechanics that we discussed in one of the previous classes. Okay? So we'll do normalization and we'll calculate probabilities and expectation values, which quantum mechanics allows us to calculate using certain rules which we discussed in the postulates, and we'll check one previous question which was asked in relation to this. So in the first question, we are asked to find A in the states represented by the following equations. Right? So we are assuming that the state is expanded in an orthonormal basis. What do we mean by orthonormality? We say that two states are orthonormal if this relation is satisfied. Okay? Phi I with phi j, the inner product is delta ij, means it's 1 if it's the same vector and it's 0 if these are the different vectors. All right, so we are given three states like this. All right, so what we do in such problems is that we'll find A by assuming that the state is normalized. All right, what's A such that the state is actually normalized? So here they have just written psi, but we will write it in bracket notation. So psi, the inner product with psi is equal to 1. This is what we will demand, and we'll assume that the basis is orthonormal. Okay, this is how we will solve these problems. Okay, so in the first case, the normalization condition here implies that okay, you could actually expand this and do this, but when you do this, what you will get because of this orthonormality is the follows, because phi 1 with phi 1 is 1, etc., and phi 1 with phi 2 is equal to 0, etc. What we will get is basically, when you do this, the equation you get is this, all right, C1 square. So we are given a state generally of this form, summation over I Ci phi I, where this set phi I is a complete set of orthonormal bases. In that case, psi with psi, all right, you can see that this is equal to modulus Ci square, and this is summed over I, all right, which means modulus of C1 square plus modulus of C2 square plus modulus of C3 square, etc. So that's exactly what we do here. We take each of the coefficients and find the modulus square, add and demand that this is equal to 1. All right, that's just what we do here. All right, this is modulus of C1 square plus modulus of C2 square plus etc. This is equal to 1 because the total probability has to be equal to 1. That's what we are demanding. We are normalizing the given state. All right, and this gives a square by 2 plus when you square this, all right, this is equal to 1, and by solving this for A, you can find A. All right, so here we see that A is equal to 1 in the first case. All right, so the normalized state in this case is 1 by square root of 2 phi 1 plus root 3 by 10 phi 3 plus root 2 by 10 phi 5. Okay, that's what's happening here. All right, so we may wonder what happened to phi 2, phi 4, etc. It doesn't matter. The state is given like this in this case. All right, the state is given like this. That's all. Okay. Maybe their probability coefficients are 0, or we have chosen an orthonormal set by the process called Schmidt orthogonalization. It doesn't matter. This is the state given. So we assume, usually it's given, it's stated that this is a set of orthonormal bases, and even if it's not stated explicitly, we can make that assumption. All right, it's all right to make that assumption, because given any set of complete set of vectors, we can always form an orthonormal set from it. Okay, so it doesn't really we don't lose any generality by assuming that this is an orthonormal set. All right, we don't lose any information, etc. And in the second case, so what we do is modulus of A square plus modulus of 2I square plus modulus of 3 is modulus of 3 square is equal to 1. That's what we demand. So when there's a complex number here, you have to be careful, because what we mean by modulus of C square is actually C star C. All right, for a real number, it's just the square, but for a complex conjugate, what we mean by the modulus square of a complex number is just this. You take the complex conjugate and multiply. Okay, so in this case, modulus of 2I square means actually, what we mean by this is minus 2I multiplied by 2I. Take the complex conjugate and multiply. Okay, so that's 4 in this case. Minus I multiplied by I is equal to plus 1. Okay, that's exactly what we do here. We get A square. So this is 2 square is 4. Okay, and here we have got a 9. Okay, so A square plus 13 is equal to 1, and from that you find A is equal to I square root 2. So as we said earlier, this expansion coefficients, all right, they can be complex numbers. They are complex numbers. These are called the probability amplitudes, and we call them probability amplitudes because taking the modulus square gives you the probability. Okay. All right. In the third problem, what do we have in the third problem? It's not very difficult. We have got a by root 2 and 2 by root 2 as the coefficients, or 2i by root 2 as the coefficients. We do exactly the same thing and we get this answer. Okay, you can check these things at home. What we have in the fourth problem, it's a similar thing. All right, so we get an equation for the square of this, and from that we can find a, the expansion coefficient. All right, so the only thing you have to remember is that when you take a modulus square of the complex number, you should not forget to complex conjugate and multiply. Okay, this is generally the C star C, where star stands for complex conjugation operation. Okay, so in some problems, okay, we may need to normalize the state before we carry on, because only when we normalize, only after we normalize, we can say that the expansion coefficient squares are associated with, are equal to the probabilities. All right, without normalizing the state, if you do, you get wrong probabilities, because the probabilities have always to add up to 1. Okay, I hope that's clear. It's not very difficult. Let's go to a second problem. A quantum state is given by this thing. Okay, and h phi 1 is equal to epsilon phi 1, h phi 2 is equal to 2 epsilon phi 2, h phi 3 is equal to 3 epsilon phi 3. Okay, these are the eigenvalue equations. These are the eigenvalue equations. Calculate the probabilities of finding the particles in state phi 1, phi 2, phi 3. Okay, so these were part of the basis, the basic postulates that we explained. So before you make a measurement, right, before you make a measurement, so here assuming that h is the Hamiltonian, you don't have to assume, I'm just giving an example, assuming that h is the Hamiltonian, all right, and what we have done is that we have taken the state of a quantum mechanical system and expanded it in the eigenfunctions, okay, using the eigenfunctions or eigenvectors to speak, eigenvectors of h cap. All right, so the basic idea was that the operators that we use in quantum mechanics are usually Hermitian operators, and the eigenvectors of a Hermitian operator can be chosen as a basis because they form a complete set. You can always construct an orthonormal basis set from the eigenvectors of a Hermitian operator. All right, so here, so what happens before measurement? This is the state. Okay, it's nice to have the skets around here, so let's put them. It doesn't really matter. Okay, so in the beginning, these are the states. Okay, so this is the state psi. The state is completely known. Okay, before you make a measurement, it's in a superposition state. All right, it's in a superposition of states phi 1, phi 2, and phi 3. This is what we call as superposition. Okay, but when we make a measurement, all right, we need the idea of superposition in order to explain or describe the quantum mechanical measurements, the results of measurements. But whenever we make a measurement, we never see the system in a superposed state. Okay, what we get is that we either find the system in the state phi 1 or in the state phi 2 or in the state phi 3. All right, and quantum mechanics gives you the probabilities for finding this. Okay, quantum mechanics gives you the probabilities for finding this, and the probabilities are given by probabilities are proportional to the modulus square of the expansion coefficients. Okay, I hope that's clear. We had discussed these things, so I was just repeating the basic ideas. So let's first check whether this is normalized. Okay, whether the state is normalized. How do we do that? We find psi with psi, the inner product. All right, so what happens? We assume that this is an orthonormal basis set. So what we have is here 2 by 9, the square root, the modulus square, okay, plus 3 by 9 plus 4 by 9. Okay, this is actually modulus square of this plus modulus square of this plus modulus square of this. Okay, we check whether this is equal to 1, and what do we see? It's 2 plus 3, so this is equal to 1. Okay, 2 plus 3 is 5 and 5 plus 4 is 9, 9 by 9 is 1. So that's normalized. The state is normalized. Now, if it's not normalized, you should start by normalizing the state, okay, or you'll get a wrong answer. Now, calculate the probabilities of finding the particle in the states phi 1, phi 2, phi 3. Now, since this is a normalized state, we can say that the modulus square of the expansion coefficients gives you the probability. Okay, so the probability of finding the state in the system in the state phi 1 is actually modulus square of the expansion coefficient. All right, that's one of the postulates that we described. Okay, so what's the probability of finding the system after measurement in the state phi 1, the probability is actually 2 divided by 9. Similarly, for this it will be 3 divided by 9, which is 1 by 3, and in this case it would be 4 divided by 9. So the probability for finding the state in phi 1 is 2 divided by 9. To find the system after measurement in the state phi 2 is 1 by 3, and you will get 4 by 9 probability for finding the state, finding the system in the state phi 3 after measurement. Alright, so the measurement actually changes the state of the system in quantum mechanics. That's important. Right? Now, after measurement, if you see that the energy measured energy is epsilon, the eigenvalue epsilon, then we know that the system is in the state phi 1 after measurement. Okay. All right, I hope that's clear. Find the average energy of the system. Find the average energy. So how do you find the average energy? If you know the probability, you can find the average energy like this. It's P1 E1 plus P2 E2 plus P3 E3. What are the probabilities? We already have the probabilities. So this is equal to, you could actually do this thing. Okay, you could actually do psi h cap psi. Okay, you could do this. You can substitute these values. You can substitute for psi in terms of phi 1, phi 2 and phi 3 and do it, and finally you will see that it boils down to this expression. It's P1 E1 plus P2 E2 plus P3 E3. We have discussed this in the previous classes. Okay, if you don't remember, you can just go and check. So what's P1? What's P1? P1 here is it's 2 by 9. All right, so the average value, let's say the expectation value of the Hamiltonian, or the average energy. Okay, the average energy is, what's the probability for finding energy epsilon? It is 2 divided by 9. Am I right? So this is 2 divided by 9, and E1 is epsilon. Okay, what's P2? It's actually 3 divided by 9. So that is 1 divided by 3. And what's the energy corresponding to this state? What's the energy corresponding to this state? It's given the eigenvalue equation. From the eigenvalue equation, you see that the energy corresponding to this state is actually 2 epsilon. And what's the energy corresponding to this state? Okay, it's an energy eigenstate, so it's 3 epsilon. So the probability is 4 by 9, 4 divided by 9 multiplied by 3 epsilon. Let's you add all this and get the answer. Okay, so the final answer is 20 epsilon divided by 9. Okay, so that's exactly what we have done here. Okay, so there's no 1, it's 2 divided by 9 epsilon, and the energy here is 2 epsilon multiplied by 3 by 9 plus 3 epsilon multiplied by 4 by 9. We have calculated the probabilities here. Okay, I hope that's clear. Such problems can be asked and you should be able to answer it really quickly. The third problem, a particle is in the normalized state. So it's given that the state is normalized, okay, normalized state psi, which is the superposition of the eigenstate with energy E0 is equal to 10 electron volt and E1 equal to 30 electron volt. Find the average energy of the following states. So two states are given. Okay, all right. So anyway, it's a good thing to check if it's really normalized. All right, so if it's in this state, let's check whether it's normalized first. So you take the modulus square and add and check if it's equal to 1. You take the modulus square of each of the expansion coefficients. In this case, it's 1 by 2 plus 3 by 4. Okay, is this equal to 1? Yes, right? So you take 4 here. So you see that it's equal to, is it not normalized? 3 by 4 plus 1 by 2. This is not normalized, okay? This is not normalized. Alright, so maybe we have to be a bit more careful here because the state here is not normalized, right? Because it's 1 by 2 plus 3 by 4 is not equal to 1. Okay? So maybe there's a problem with the question. If we put instead of 1 by square root of 2, if we put a 1 by 2, so let's take the state as 1 by 2 E0 plus square root of 3 divided by 4 E1. Okay, that's normalized now because when you square and add, you get 1 by 4 plus 3 by 4 is equal to 1. It's normalized now. Alright. Now, if you want to continue with this state, you just have to normalize. How do you normalize this state? We have already done the problem to find, to normalize this. How do we normalize this? Alright. So, we check what's 1 by 2 plus 3 by 4. Okay. Modulus square of these things, and we see that it is actually is equal to 2 plus 3, that's equal to 5 by 4. Okay. So they say that the probability, when you square and add, you get 5 by 4. Right? So what we do is that we divide each of the coefficient by square root of 5 by 4, or we divide each probability by 5 by 4. That would normalize it. Okay. Alright. So if you want to calculate the probability for finding energy E0, you should have to take 1 by 2, and then, so you could ask this question, alright, what's the probability for measuring an energy value E0? Okay, so the expansion coefficient is 1 by root 2, so you take the modulus square, but since it is not normalized, you have to correct it by this factor by dividing it by 5 by 4, okay, or multiply by 4 by 5. So the answer would be actually 2 divided by 5. Okay, I hope that's clear. So that's how you normalize this state. Okay, so similarly, the probability for finding an energy E1 would be 3 by 4 multiplied by 4 divided by 5, and that would be equal to 3 by 5. Okay, so this is how we do such problems. So let's continue with the answer. Okay, let's continue with the problem here. We need to find the average energy. We need to find the average energy. Okay, so we just got carried away a little bit. Let's come back to the problem. Let's find the average energy. All right. So I was right. So this square root is a mistake here. It was not there. You see that its P0 is 1 by 4 and P1 is equal to 3 by 4. Now it's normalized. All right. What's average energy? It's P0 multiplied by E0. Okay. This is actually P0 multiplied by E0 plus P1 multiplied by E1. That's 25 electron volts. Okay. In this case, it's 1 by 3 multiplied by 10 plus 2 by 3 multiplied by 30. So it's 70 divided by 3 electron volt. Okay. So what do we mean when we say that these are the average energies? Okay. So this means that if you prepare the state, okay, if you prepare, so let's stand. So if you prepare the state in the system, an electron in this state, for example, okay, you have to make a large number of identical copies of this state. Alright, you prepare a large number of electrons, so quantum mechanical system in this state, and on each system you make an energy measurement. On each separate system you make an energy measurement, you will get a value. Alright, so if you add all these values and divide it by the total number of measurements, okay, you should get, if the number of, you should actually make a large number of measurements, okay, so then the answer would be this according to quantum mechanics. It would be 70 by 3 electron volt. That's the average energy, the average of all the measurements that you make, okay, all the energy measurements that you make. Okay, I hope that's clear. Now, yeah, that's what it means. Okay, so here is the fourth question. The wave function of a particle is given by psi is equal to 1 by root 2 phi 0 plus I phi 1. So this is a previous net question. So phi 0 and phi 1 are the normalized eigenfunctions with energies E0 and E1 corresponding to the ground state and first excited state respectively. All right. The expectation value of Hamiltonian in the state psi. Okay, you need to find the expectation value of Hamiltonian in the state psi. Okay. How do we do this? We first check whether this is normalized. It's important. Right? We first check whether it is normalized. Is it normalized? So we see that 1 by 2 plus what is I? Modulus of I square, that's I star I, which is equal to 1. Okay. So we see that this is equal to 3 divided by 2. It's not equal to 1. 3 divided by 2. So if these probabilities have to be normalized, you can take the modulus square, okay, of each coefficient and then divide it by 3 by 2. Divide it by 3 by 2. Then the state, then the probability, then we are using a normalized wave function. All right. Or you can find the normalized wave function like this. Let's say psi normalized, okay, is equal to 1 by root 2 multiplied by square root of 2 by 3. Okay, we are just dividing by the square root, all right, plus I multiplied by square root of 2 by 3. Okay. Now you can check if this state is actually normalized. You take the modulus squares and add. Okay, you should get 1. That's what we did actually. So we can check for consistency. This is equal to 1 by 2. Okay, so if we do psi n, okay, this is 1 by 2 multiplied by 2 by 3 plus 2 by 3 multiplied by 1. Okay, what do we get? It's equal to 1 by 3 plus 2 by 3 equal to 1. So this state is now normalized. Okay, this is how you normalize a state. All right. So this factor we can say is the normalization factor here. Okay, we have to normalize the state. Okay. Now once we normalize it, so we know how to normalize the state now. What's the expectation value of the Hamiltonian in the state psi? Okay, that's the question. So how do we find the expectation value? As I said, you take the probability. So the energies are given, the probabilities are given. All right, you take the probabilities. The probability for energy E0 is, finding energy E0 is 1 by root 2 square. Okay, modulus square of 1 by root 2. All right, multiplied by this 2 by 3. Okay, E0. This is the probability for finding energy E0 and measuring energy value E0, and the probability for measuring energy value E1 is actually, we see that it's modulus of I square multiplied by 2 by 3. Okay, multiplied by E1. So this is the expectation value of the Hamiltonian. All right, we can just simplify this, and what we get, there's a square here. Right, because only then it becomes a probability. So this is 1 by 2 multiplied by 2 by 3, that becomes 1 by 3 E0 plus modulus of I square is 1 plus 2 by 3 E1. Okay, so it's actually E0 plus 2 E1. Sorry, I should write it here. It's E0 plus 2 E1 divided by 3. So it's option D. Okay. The next problem is this one. Consider a particle in one-dimensional potential that satisfies V of x is equal to V of minus x. Right? V of x equal to V of minus x. Right? Let psi 0 and psi 1 denote the ground state and first excited states respectively. Okay, the state is given, psi is equal to alpha 0 psi 0 plus alpha 1 psi 1. Okay, it's a normalized state with alpha 0 and alpha 1 being real constants. The expectation value x, or the expectation value of x, which means the average value of the position, the measurement of position operator x in the state, psi is given by. Okay, what's the average value of this position? All right, so we can start with the basic definition. We can say that the expectation value of x is actually psi x cap psi. Okay, now we are given psi here. Psi is equal to alpha 0 psi 0 plus alpha 1 psi 1. Okay, which means that the corresponding bra, okay, we know the rule to make bra. If you make a ket into bra, the complex numbers, okay, have to be replaced by the complex conjugate. So this would be alpha star, and kets here would be replaced by bra. Okay, we have discussed these things. So this would be alpha 1 star psi 1 in that form. Okay, yes, so that's fine. Now we just combine this. Okay, now we just combine this. What's the expectation value of x? That's equal to, let's say, alpha 0 star bra psi 0 plus alpha 1. Oh, wait a second. It's given that this alpha 0 and alpha 1 are real. Okay, these are real constants. So we can omit this star here because these are real numbers. Okay, if you take a complex conjugate of a real number, you get the same number. All right, here so it's psi 1, so we don't need the star here. You can put the star if you want, but finally it doesn't matter. You have to get rid of it anyway because these are real numbers. Okay, now we have got an x cap here, and then ket psi, that's alpha 0 psi 0 plus alpha 1 psi 1. All right, this is the thing, this is the expectation value. Now we can actually combine these terms. Okay, there are 4 terms in this expansion. We will expand before doing anything else. So this would be alpha 0 square. So we take this alpha 0 psi 0 bra psi 0 x cap alpha 0 ket psi 0. Right, so this alpha 0 is a number, you can pull it out. So it's alpha 0 square psi 0 x cap psi 0 plus the next is you combine this with this. Okay, so that becomes alpha 0 alpha 1 psi 0 x cap psi 1, okay, plus alpha 1 psi 1. Okay, we got combine this, we have got an x cap here. Sorry, there was this alpha 1 and alpha 0, so we can pull it out together. Alpha 1 alpha 0 psi 1 x cap psi 0. We are just combining these terms, all right? This is how it's easy to combine. You just put them together, that's all, okay? Because the rule for multiplication is given in this, okay? The bracket is the scalar product. So basically we are taking scalar product, etc. here. So this is why the Dirac notation is much easier to use, okay? We can just add this or put these terms together and you get the result, okay? So yeah, alpha 1 alpha 0 alpha 1 alpha 0 psi 1 x cap psi 0, fine. There's one more term, plus alpha 1 square psi 1 x cap psi 1, all right? So we haven't done anything here. The state is given. This is the state of the system. The state is given. So this is the bra corresponding state. This is the state of the system, okay? Psi is the state of the system. We just did this thing. We found the we just expanded the rule for the expectation value, okay? And we see that there are 4 terms here. Okay. What do we do now? So now we see that there's an extra information given here. It's v of x equal to v of minus x. There's an extra information given here. V of x equal to v of minus x. Okay, which means that the potential energy is the same. Let's say, for example, at x equal to minus 1 and x equal to plus 1. This means that the physical conditions are exactly same for x equal to minus 1 and x equal to plus 1. Similarly, x equal to plus 2 and x equal to minus 2. The potential energy is the same, or the physical conditions are exactly the same, right? So this means that, so we don't go into the details, but this means that the probability for finding the particle at x equal to minus 1 has to be equal to the probability of finding the particle at plus 1, because the physical conditions are exactly the same, all right? By this equation, it means that the potential energy is the same at x and minus x, all right? 1 and minus 1, 2 and minus 2, etc. Okay, this means that the physical conditions are exactly same, for example, at x equal to minus 1 and x equal to plus 1, x equal to minus 2 and x equal to plus 2 for all x like that. Okay, this means that the probabilities for finding x equal to, let's say, some value x equal to a and x equal to minus a, probability of finding the particle at x equal to a, let's write it like this, all right, has to be equal to p of x equal to minus a. All right, so we have just used a physical intuition here. Since the conditions, physical conditions are exactly same at x equal to a and x equal to minus a, the probability of finding the particle at x equal to a and x equal to minus a have to be the same. All right, this is just an example. So this is true for all x. Okay, the probability of finding the particle at x will be exactly equal to the probability of finding the particle at minus x. What does this mean? Okay, suppose you make the position measurement. This means that if you measure the position, all right, and suppose you found the particle at, or the electron at the position x equal to minus 1 5 times. You are making a large number of measurements. That's the meaning of finding the average. You're making a large number of measurements, and you find the particle at, for example, or let's say minus a for any a, all right. Suppose you found x equal to minus a. When you make the measurement of the position, you see that it's at x equal to minus a, let's say 100 times. 100 times, so you're making a large number of measurements, and 100 times you found the particle at position minus a, x equal to minus a, all right. This means that since the physical conditions are the same, you will also find the particle at plus a the same number of times. Okay, this is the meaning of saying that it has got the same probability. It has you have got the same probability of finding the particle at a and minus a. Okay, so when you average, when you take the average, what do you do when you take the average? We take all the measured values and add them. All right, you take all the measured values and add them. So when you take all the measured values and add them, you see that this contribution will exactly cancel to this contribution, right? Cancel with this contribution, right? Because here the experimental outcomes are numbers like this. Okay, the position, the experimental outcome is a number, right? So if you take the measurement, the result, the measurement result for position, you will see that the contribution from this position exactly cancel, right? Because you'll find, let's say if you find x, the particle at x equal to minus a 100 times, you would find the particle at plus a also 100 times. Okay, suppose like that. So when you add this, this will exactly cancel. All right. This means that if it's in the same state, all right, if it's in the same ground state, if it's in the same state, this is the ground state and this is the first excited psi 1. All right. If it's the same state, the probability for finding the particle at x equal to plus a and x equal to minus a are the same. So when you take the average, they will cancel each other. Right? These numbers will cancel each other. This means that this expectation value can be taken as 0. Okay, we have used the physical information that the physical conditions are exactly same. Okay, all right. So this is 0. All right. So we can say, so for example, okay, if that's not clear, I'll just elaborate a little bit. When you make a probability, when you want to calculate the expectation value, all right, let's say you are calculating it experimentally. Okay. So when you calculate experimentally, what you do is that you prepare a large number of systems identically in this exact same state. Okay. Then you start measuring position. That's what's happening. Okay. So this corresponds to the expectation value of x in the state psi 0. What happens? So let's say the probability for finding x equal to a is, let's say this probability, x equal to a, or we can say probability of a, probability of x equal to a, all right, x equal to a is exactly same as probability of x equal to minus a, all right. So let's just take the contributions from these results, all right. So when you take the average, the contribution from x equal to a and these results would be p of x equal to a, that's a probability corresponding to probability for measuring the particle at x equal to a multiplied by a. Okay, just like we did in the previous case, p1 a1 plus p2 a2 etc. Here it's probability for finding the particle at x equal to multiplied by a plus probability of finding the particle at x equal to minus a multiplied by minus a. All right. So since these are same, these are equal. Okay, we said why these have to be equal. This contribution becomes 0. Okay, this contribution becomes 0. I hope that's perfectly clear. If not, we'll understand it later on. All right, that this will actually be the case. Okay, this means that we can put this equal to 0 and also this equal to 0 if it's in the same state. All right. So we only have the cos terms here. We only have the cos terms here. Right. So the answer should be alpha 0 alpha 1 psi 0 x cap psi 1 plus alpha 1 alpha 0 psi 1 x cap psi 0. Okay, that's exactly what we have got here. Was the answer? It's this one. All right, it's alpha 0 alpha 1 psi 0 x psi 1 plus psi 1 x psi 0. Okay, the coefficients are the same. I hope that's clear. Okay, so the only thing is that we used a physical argument here without going into details. We used a physical argument here because v of x equal to v of minus x. This means that the physical condition at x are exactly equal to physical conditions minus x. So the probabilities of finding the particle at x has to be equal to the probability of finding the particle at minus x. So when you average it, the terms will exactly cancel. Right? So if it's in the same state, if you are finding the expectation value in a state psi 0, that has to be equal to 0 also in psi 1. All right, but there's no reason for this term to be 0, for example. Okay, this term is not equal to 0. There's no reason for this term to be 0 by this argument. All right, so that's the answer. Okay, we have got alpha 0 alpha 1 psi 0 x psi 1 plus psi 1 x psi 0. Okay, I hope that is also clear. Now with that we'll conclude today's session. I shall see you in the next session. Thank you.